In this video, we are going to continue on working with L'Hopital's rule by looking at a few more indeterminate forms. And keep in mind, L'Hopital's rule originally was used to evaluate limits where we had these forms 0 over 0, infinity over infinity, because those are not quantities that have any meaning associated with them. As we've seen in our previous examples, 0 over 0, infinity over infinity, in the sense of a limit, can actually take on any value. Similarly, other indeterminate forms would be things like 0 to the 0, there's no meaning, infinity to the 0, or 1 to the infinity. And whenever we see an indeterminate form of one of these three types, our goal is going to be to rewrite algebraically so that we can somehow get back to those original indeterminate forms. So let's look at a motivating example. The limit as x approaches 0 from the right of x to the x. So as x goes to 0, x goes to 0. So this is an indeterminate form of type 0 over 0. And the motivation I'm going to have here is I'm going to think about if I wanted to differentiate this function x to the x, how would we have to rewrite that? We would rewrite it using properties of exponentials and natural logs. We would say this is equivalent to e to the natural log of x to the x. And then I'm going to do kind of two things at once here. One, remember that an exponential is a continuous function, so we can actually take this limit and move it inside the exponential. So I can write this as the exponential e raised to the limit as x approaches 0 from the right. And at the same time, I'm also going to note that this exponent x that was maybe causing us trouble, once it's inside the natural log, you can pull that out front. So this becomes x ln of x. And this should actually be a familiar example, one we evaluated in a previous example. As x goes to 0 from the right, we'll have x goes to 0, and as we approach 0 from the right, natural log x goes to minus infinity. And whenever you see this indeterminate type, now it becomes 0 times infinity, we know we are in a good position because we can rewrite algebraically. So this is e to the limit as x approaches 0 from the right of the natural log x divided by 1 over x. As x goes to 0 from the right, ln goes to minus infinity, 1 over x goes to infinity. And we now have the desired indeterminate form, and we can apply L'Hopital's rule. So e raised to the limit as x approaches 0 from the right, we differentiate in the top, and we divide by the derivative in the bottom. And algebraically, dividing by a fraction is equivalent to multiplying by its reciprocal. So now just simplifying, this is the limit as x goes to 0 from the right of minus x. The value of that limit is 0, and e to the 0 is equal to 1. So as an overview, if we have one of these new indeterminate forms, 0 to the 0, infinity to the 0, 1 to the infinity, these are things with no meaning individually, but what we can do is use properties of exponentials and natural logs to rewrite. And notice, what happened here, kind of the general form that we can expect to see is if you have f of x raised to the g of x, this is equal to e to the natural log of f to the g. But that exponent g is always going to pull out in front of the natural log. So we will typically jump immediately to that step. So let's look at a similar limit. The limit as x approaches 0 of the function cosine x raised to 1 over x. So in this case, we're thinking as x goes to 0, cosine itself is going to 1. And as we approach 0, we can think of 1 over x as going to infinity. So this is an indeterminate form of type 1 to the infinity. So in order to get to the point where we can actually apply L'Hopital's rule, we need to rewrite algebraically. So using properties of exponentials and natural logs. This becomes e, and then we'll have natural log of cosine x raised to that 1 over x power, but a power inside the natural log can be pulled up front. Additionally, we've seen we can take this limit and move it inside a continuous function, which the exponential is. So it's a limit as x goes to 0 of the natural log of cosine x divided by x. As x goes to 0, cosine of x goes to 1, and the natural log of 1 is 0. So ln of cosine x is going to 0, x is going to 0. So once we've recognized that we have this new indeterminate form, we rewrite using properties of exponentials and natural logs, and immediately we end up in a good position, one where we can apply L'Hopital's rule. So L'Hopital's rule tells us that for this limit we have, we can take the derivative of the top, divide it by the derivative of the bottom. So the derivative of x is 1, that's the easy part. To differentiate the natural log of cosine x, we use a chain rule. So we take the derivative of the outside function, 1 over, evaluate at the inside function, and then we multiply by the derivative of the inside function. And the derivative of cosine is minus sine. Now as x goes to 0, we have something that we can evaluate. Sine goes to 0, cosine goes to 1. So now the top is going to 0, the bottom is going to 1. This ends up being e to the 0, and e to the 0 is equal to 1.